Thank you. Can you hear me well? I'm using the microphone. Is it okay? No, not really? Good. Okay. Okay. So my plan is first to talk about neutron stars in general, to give you kind of general introduction, to remind what neutron stars are. Okay? And then I will talk more specifically about magnetars. So the plan is to have 4 lectures on this topic. And maybe it will be 3 + 1, where the last one would be more on radiative process. We'll see how we go. So first, this is a list of things neutron stars are responsible for in the universe. The approximate list that highlights the main activities of neutron stars. I don't have a pointer, so we have to, I will try to guide it through the list. I think it should be easy. So first, they can be observed as radio and gamma ray pulsars. Okay? These are the among brightest sources in our galaxy, and they also feed bright nebulae, in particular Crab Nebula. They can produce giant flares. This is magnetar-like activity, which I talk much more about in more detail later. Of course, they can accrete. If neutron stars accrete, they turn on as bright sources of X-ray emission. And again, if you just look in the sky, in X-rays, you'll see lots of accreting neutron stars. They can produce gamma ray bursts, okay? And they can also produce non-trivial heavy elements that I think Francois probably talked about already, and Samaya will talk much more about, I think, today. So it's quite an impressive list. And let me start with very basic stuff, just to remind you, just take it easy. The simplest picture of a neutron star. Okay, so neutron star has a mass of roughly 1.4 solar mass. And if you calculate how many nucleons it contains, you just divide by the proton mass, which is 10 to the minus 24 grams. The solar mass is 2 times 10 to the 33 grams. So you divide the two numbers, you get the baryon number, 10 to the 57 nucleons. So essentially what neutron star is a gigantic nucleus where this number, 10 to the 57 nucleons, are packed together all the way, you know, the densest basically possible configuration, to the point when they start to repel each other due to nuclear interaction. So basically, each nucleus has size 10 to the minus 13 centimeters. As you know, you pack them together to that nuclear density. And so you can immediately estimate the radius of a neutron star from this. You just take a radius of one nucleon, 10 to the minus 13 centimeters, take 10 to the 57 nucleons, pack together, get radius of 10 kilometers. That's basically what it is, a neutron star. To remind you, neutron stars were predicted very soon after discovery of neutrons, a couple of years after discovery of neutrons. And it was a bright prediction that was confirmed significantly later. Basically, it was speculated that to power a supernova, the collapse of a normal star into such a compact object as neutron star is will immediately give you enough energy to power a supernova. Okay, so you just take a star, let it collapse to a radius of 10 kilometers. You can calculate how much gravitational energy you release, and you find that this energy is huge, of course, because you contract, gm square over r. R is small, m is large. You get large energy that you can release through collapse, and this energy is what you miss. It's an important ingredient for supernova explosion. So when the star, it was speculated by Ziki that you produce neutron stars in the end of stellar evolution. Now again, basic stuff to remind you that any star is supported by pressure, right? So you have competition between gravity and pressure gradient. Pressure has to offset the gravity that tends to compress the star, and pressure tries to expand the star. So the balance between the two is the hydrostatic balance. So normal stars are supported by thermal pressure, right? It can be pressure of gas, just P is nKT, or massive stars, it could be radiation pressure, AT to the 4th divided by 3. When you look at more compact objects during cell evolution, as I hope you remember, as the star evolves, it forms a dense core, which is going to become white dwarf later when the star loses its envelope. And this core, or later the white dwarf, is supported by the electron degeneracy pressure, which is completely different from thermal pressure, right? So how to estimate the hydrostatic balance in this case? Well, you just calculate the Fermi momentum. So degeneracy pressure means that thermal motions are not important. What is important is the Pauli uncertainty principle. Particles are squeezed in the spatial direction, and they're pushed in momentum space, so that the phase volume that they have available is not smaller per particle, it's smaller than h, the Planck constant. So if you squeeze in spatial dimension, you push particles in the momentum direction, and they become energetic. So they have to move. That's the source of pressure. That's the degeneracy pressure. At zero temperature, you can forget in this regime about temperature, you push particles to high and high energy levels. And if at zero temperature, you basically occupy all the states, the quantum states, right? And then you come to the Fermi level. P Fermi is this upper boundary, the Fermi momentum, which is given by that simple formula. Pf is 3 times h bar, the Planck constant, times the electron density to the 1/3. So that's the characteristic momentum of electrons in the white dwarf. And once you know the momentum, you know energy, Pf squared over 2 electron masses, and you equate it to find the approximate hydrostatic balance. You just equate this characteristic energy per particle per electron, you equate with gravitational energy. That's the hydrostatic balance condition. Okay, the only subtle point is that gravity is sensitive to mass. So actually gravitational force is applied to protons, while pressure is communicated through electrons. But of course they're coupled. Protons cannot move separately from electrons. They have to maintain neutrality. And so the star is basically electron pressure. Proton mass hangs on electron pressure, if you like. Now, there is a limit to this configuration, which is the famous Chandrasekhar limit. Maybe you can tell me, actually, when does this, what corresponds to the Chandrasekhar limit? What is the simple condition, looking at just at this formula, what is the, how to formulate the maximum mass of a white dwarf? What is the physical condition that it corresponds to in terms of these equations? Yeah.
When the Fermi momentum is like the speed of light.
Exactly, relativistic, right. So that equation, this energy Pf squared over 2me is only applied to non-relativistic electrons, right? That implies certain equation of state, because we see that P Fermi scales with density to the 1/3. And sorry, P Fermi is density to the 1/3, P Fermi squared is density to the 2/3, and that supplies the 5/3 adiabatic index for the non-relativistic degenerate gas. Once electrons become relativistic, energy is approximately speed of light times P Fermi. So now energy per particle scales as density to the 1/3, not 2/3. And that leads to adiabatic index of 4/3. And this configuration is unstable. Okay? So that's simply, that's how you get the Chandrasekhar limit. So the maximum mass of a white dwarf is obtained simply equating P Fermi to electron mass times the speed of light. And then you derive the nice formula, which it turns out to be close to the solar mass. Okay, so neutron stars, of course, when the white dwarf collapses, it's going to form a neutron star. And that's the kind of mass that you expect for a neutron star. The funny thing that it is comparable to the solar mass. It wouldn't have to be. Okay? And also it's funny that actually you can see that the solar mass happens to be basically Planck mass cubed divided by the proton mass squared. There is no reason for that if you think about it, right? So what is written here to the power of 3/2 is essentially Planck mass cubed. That's a characteristic mass that is made of Planck constant, gravitational constant, right, and speed of light. It's called Planck mass. And so what the white dwarf limit is the Planck mass cubed divided by the proton mass squared, which is also the solar mass, 2 times 10 to the 33 approximately grams. Just funny observation, right? Okay, so all that stuff was realized a long time ago. Stoner first, 1922. Then the famous Chandrasekhar work, 1931, and Landau, 1932. Now, that's the characteristic maximum mass of a white dwarf, beyond which it collapses to a neutron star. Now, the next question would be, what's the maximum mass of a neutron star? And I wrote there 3 solar masses. Do you know what sets? I mean, what would be the simplest upper limit to a neutron star mass? White cannot be 15 solar masses. What's the simplest way to argue that neutron stars cannot be too heavy, not 100 solar masses? Yeah, right. So the gravitational potential could not be more than c squared, right? Because otherwise it would become a black hole. The Schwarzschild radius scale is mass. Schwarzschild radius of an object of mass m is 2gm over c squared. That's the black hole size. And so if you push mass to high values, basically your object, if you try to sustain it, ends up inside the Schwarzschild radius. So it has to collapse into a black hole. Okay? You cannot go much above nuclear density if you right. Okay, so that's the simple way of see how you arrive in this interesting range of masses. And actually what is observed is the neutron stars have mass between 1 and 2 solar masses. Now that was theoretical prediction. Of course, they're discovered as pulsars. Well, this is rather ugly pulse profile, actually. It's one of the first pulsars, and we have now much better pulse profiles, much nice observations. But even here, you kind of can see the purity is highlighted above the time profile. By now, we know about 2,500 of pulsars. Okay, and they're indeed, some of them indeed located in supernova remnants. For example, the famous Crab pulsar. So there was beautiful confirmation of the theoretical speculation that neutron stars form in supernova collapse. And they can rotate really fast. The shortest period is 1.4 milliseconds. Well, to finish this little introduction, and just I'm reminding you some basic stuff about, right? So let me also remind how you estimate the number of neutron stars in the galaxy. Basically, you tie it to the number of supernova explosions, because a large fraction of supernova explosions produce neutron stars. And we know that, roughly speaking, you have 1 supernova per century. So each one, well, a significant fraction of them leaves a compact remnant, a neutron star in particular, not a black hole. And so the outcome depends on mass. If you're like 20, 30 solar masses, you would produce a black hole. If you're above, if the progenitor star has mass above 8 solar masses, but below 20, you'd produce a neutron star. And so if you just take this rate, multiply by the age of the galaxy, whatever, 10 billion years, then you end up with 10 to the 8th remnants, 10 to the 8 Newton stars. You wanted to ask something? No? Okay. Now, what happens then? Well, when the star collapses, of course, you have enormous heating. Also, you have compressional, you pressurize the object, of course, by compression. So electrons become very degenerate. They push them to high energies. And also, there is significant thermal energy in the electrons and matter, baryonic matter. And what happens then is neutronization. So that's why you have formation of neutron stars. As you increase density, Fermi level goes up for electrons. And at some point, the electron energy becomes sufficient to let it combine with the proton to form a neutron, right? So there is a gap in mass between neutron and proton. Neutron is a little heavier, roughly it's MeV scale, 1.3 MeV, I think. And so to form a neutron from a proton, you need energy. So when your energy per electron is high enough, let's say a couple of MeV, they easily combine and emit neutrinos on the way in this reaction, and they turn into neutrons. So that's the neutronization reaction. Electron plus proton goes to neutron plus neutrino, and that's why in the end the complex remnant is a neutron star. So it's mostly made of neutrons. The typical temperature is 10 to the 11th Kelvin after they collapse, but this remnant cools very fast, mostly because of neutrino emission. So this reaction and also what they call Erka reaction, you also have lots of positrons at these temperatures, right? So this temperature, if you multiply it by Boltzmann constant, is way above electron rest mass. So KT would be something like 10 electron rest masses. So at these temperatures, you can easily produce electron-positron pairs. So you have then both reactions. You have electron capture on protons that produce neutron and neutrino, and then you have positron capture on neutrons that converts neutrons back to proton. And so in the end, the chemical composition, the ratio of neutrons and protons is set by the kinetic equilibrium between these two reactions, which is shifted toward neutrons at high density. So that's why you have in the end lots of neutrons. But it's also a cooling mechanism, because as electrons are captured on protons, they produce neutrinos. As positrons are captured on neutrons, they produce antineutrinos. And you go back and forth, and each time you emit neutrinos and antineutrinos. And they just go, they diffuse out of this remnant. They carry the energy away. So you have an efficient cooling mechanism. And later, well, neutrino cooling is very sensitive to temperature. It slows down, and at some point, the star begins to cool mainly through its surface radiation rather than neutrino. So the heat diffuses to the surface, and it's radiated from the surface, just like blackbody emission. In the end, after 1 kiloyear, when your stellar remnant is 1 kiloyear old, its temperature, internal temperature, is typically 10 to the 8th Kelvin, and its surface temperature is about 10 to the 6th Kelvin. So that's it. So basically, after the collapse, it was something dramatic, emitting neutrinos, which have been detected, by the way, right, in supernova 1987A, which I've heard about maybe in this room. No, it was another. In 1987, I was taking classes. I think it was mechanics. Yeah, I'm pretty sure it was mechanics class. And someone entered the room. It was like 100 people sitting, and asked the lecturer to stop for a second and announced that neutrinos had been detected, and this news about supernova 1987. So these neutrinos have been seen. It's not only neutrinos are seen, of course, from the sun. And they also, well, now IceCube also detected neutrinos, very high energy neutrinos, whose origin is debated right now. But from supernova explosions, neutrinos are predicted, and they have been detected, and they have the right energies that you expect, this kind of MeV energies that you expect from the explosion, from the collapse. All right, so, but in the end, what you are left with is rather boring object. You are left with basically a ball which is looks metallic from outside. It's relatively hot. Its temperature is 10 to the 8th inside, 10 to the 6th on the surface. So it does radiate some luminosity, thermal X-rays. The luminosity for this temperature you can easily calculate, black body emission, right? So you take sigma t to the 4th, that's the flux from the surface, multiplied by the area of the star, which is 4 pi r squared, 10 to the 13 centimeters squared. And you end up with a number like a few times 10 to the 33 ergs per second, which is pretty much solar luminosity. So it's a compact object which emits X-rays, but it's rather weak, and it's cooling with time. It's going to die, right? So there's nothing happening really. So why would they be interesting? Not so clear, but we'll talk about this later. So of course they happen to be the brightest actual objects in the sky. So, but before, let me just complete this discussion of cooling. So this figure shows actually somewhat uncertain theoretical cooling curve, the red curve, which shows the evolution of temperature. This temperature has infinity upper index because because of gravitational redshift you have to distinguish between temperature on the surface and real temperature measured locally and temperature of radiation that comes to infinity. There is gravitational redshift. So this is the observed temperature as a function of age of the star, expressed in years on log scale. There are uncertainties in this curve because it's sensitive to things like superfluidity. So typically the Neutron star becomes superfluid something like a few centuries after birth. Neutrons pair. And the cooling reactions are sensitive to that. Neutron star material, by the way, also becomes superconducting, so protons also pair, and then which leads to important implications for how the magnetic field inside Neutron star behaves. In particular, in the core, you expect the magnetic field to be quantized in flux tubes. It's normally what they call superconductor of type 2, when magnetic field shrinks into flux tubes. The superfluid, the neutron superfluid carries most of the mass and most of the rotational energy. And it's also quantized in the sense that rotation is quantized. It's quantized into vortices, separate vortices. And these vortices are real entities which actually can move as the star spins down with age. They move away from the axis because density of these vortices is basically controls how fast the Neutron star rotates. And so these two entities, vortex lines and flux tubes, can interact with each other in a way which is not completely understood. So it's rather fascinating object in terms of, from quantum mechanics point of view. Anyway, so the theory of cooling of Neutron stars is a bit complicated. So this plot is from Yakovlev and Perfect review in 2004. Also what you see here is data, different Neutron stars. Nearby neutron stars which are identified as thermal emitters, you can see what is the surface temperature. You can see relatively good agreement. Okay. Well, this is Neutron star structure. So it has an atmosphere, this outermost layer. Then there is an outer crust. And then as you go inside, the composition changes toward more and more neutron-rich elements. The ground state of matter at high densities is shifted toward neutron-rich nuclei. When you come to the, of course, density is increasing toward the center. When you come to the density of 4 times 10 to the 11th gram per centimeter cube, what starts to happen is neutron drip. So nuclei begins to lose neutrons, and you form free neutron liquid, which also forms a superfluid. So there is superfluid in the core and superfluid in the crust. So below this boundary is what we call inner crust, and it goes from this neutron trip density all the way to 10 to the 14 gram per centimeter cube, which is close already to characteristic density of a nucleus. This is nuclear density, basically. Then you actually go to higher densities. When you move toward the core, you go above 3 times 10 to the 14, which is already above the nuclear density. and up to 10 to the 15th, roughly speaking, grams per centimeter cube. So the equation of state at those high densities is not really known, and people try to calculate this theoretically, but there are huge uncertainties, which translates to the, of course, to the radius of the star. When you calculate hydrostatic balance, you need to know pressure, and pressure comes from the equation of state. So this diagram shows various versions of these calculations, mass versus radius. The one feature you can see, of course, that for different masses you have about the same radius, but the value of this radius is sensitive to the chosen equation of state. And gray curves are masses that, the equation of states that have already been ruled out. And simply by the fact that we see rather massive neutron stars. The maximum mass is about 2 solar masses detected so far. On the right, you can see a list of neutron stars with measurements of masses. Of course, you need a binary system to measure mass, right? Because it's the only way. You need gravitational interaction to measure a mass. And you can see that they go to 2 solar masses within an error. All right, from 1 to 2. Okay, now, so this boring, interesting from physics point of view, but observationally, naively, would say it's not particularly interesting. Okay, there is a passively cooling, compact ball of material, very dense material, but so what? But in fact, it does happen to be a bright source of radiation. So the first question I'd like to ask you, actually, can you tell me what are the possible energy sources? We observe various types of activities of neutron stars, and I want to have a list first. So can you tell me what you can think of as an energy source to switch on this passively cooling remnant as a bright source of radiation? Yes, good. That's the one I'm going to discuss in much more detail later. Magnetic field. Another one I mentioned already, residual heat from the neutron star birth. It's born with a lot of heat stored already. And as it passively cools, you see this heat comes out from the surface, partially. Most of it is emitted in neutrinos. But it's kind of trivial energy source, so it cools down. So the other one is magnetic field. The non-trivial question would be how to use this magnetic field to produce any observable luminosity, because, okay, it sits there. What else? Accretion. Yeah? Accretion. Good.
Nuclear reactions?
Nuclear reactions, which I didn't list here, but you are right. Nuclear reactions. So accretion. What else? Rotation. Rotation, yeah. Anything else? Let me see my list. One thing I added is merging the binary. Okay, I didn't mention nuclear reactions, but you're right when you have X-ray bursts that come from nuclear reactions. So, of course, by far the highest, the strongest source is the merger, right? Because in this case, you release a lot of energy, comparable to the rest mass of a neutron star. But it turns out that the other 3 or 4 are also interesting. And I'll briefly discuss in this first lecture, discuss briefly rotation and mention accretion and magnetic field. And then we'll move on to magnetars. So, okay, so rotation is rather trivial energy source, right? The star is rotating. Of course, the star is born with magnetic field, with angular momentum, and it's conserved during the collapse. And conservation of angular momentum implies significant amplification of kinetic energy. Because angular momentum is I omega, it's conserved, right? So if I goes down, I is the moment of inertia, is this roughly mass times radius squared. As radius is compressed, I goes down as radius squared. To conserve angular momentum, omega has to go up, inversely proportional to I. But energy goes as omega squared. So energy is amplified significantly. And if you look at the typical period, it could be even rotating even faster, let's say 10 milliseconds after the birth of a neutron star, then you have a lot of energy, 2 times 10 to the 50 ergs, just sitting in rotation. If you find a way to extract it, it can be a bright source of radiation, right? So simple. Now, how do you extract it? Of course, rotation by itself does not, convert to photons or anything observable. You need something else. What you need is a magnetic field of the star. But we do see this rotational energy appearing beautifully in the Crab Nebula. Just to remind you that one of the beautiful discoveries in astrophysics is that when you look at the Crab Nebula, calculate how much power comes from the nebula, and compare it with the energy that you see disappearing from the central rotating pulsar, the Crab pulsar, which has 33 millisecond period, and it slowly spins down, then you know the Neutron Star moment of inertia. It's about 10 to the 45 in CGS units, multiplied by omega squared, which you know from the period. Then you measure how the omega is changing with time. Radio observations are very sensitive, so they can measure this p dot, time derivative of the period of rotation. You see how much kinetic energy disappears from the central object, and the same energy is appearing in the Crab Nebula in the form of synchron radiation. So it's obvious that the energy, Shklovsky first suggested that the energy comes from, the Crab Nebula is fed by rotational energy of the central star. And you see now, we have now this beautiful image in X-rays, Chandra image, which shows a non-trivial structure of this nebula in X-rays. There is a jet and there is a torus around it. So this wind that supplies energy from the pulsar to the nebula has an interesting non-trivial structure, and there are interesting open questions related to that, but I'm not going to discuss it today. Of course, to extract energy, like I mentioned, you need magnetic field, but that's pretty much it. So it's still a very simple thing. So you have a sphere, it's rotating with some omega, and it has a magnetic dipole moment. Magnetic field is strong for the same reason. When during the collapse, magnetic flux is conserved, so magnetic field B times radius of the star squared is constant during the collapse. So as R goes down, B goes up. And energy that you have in magnetic field, by the way, goes as B squared. It goes as R to the 4th, by the way. Okay, but what's important for the extraction of rotational energy is that you have now a simple mechanism of producing Poynting flux from the object. So when you have magnetic moment, which is not aligned with omega, it's rotating, right? So mu is changing direction, and you have to produce magnetodipole radiation, just like you produce when you have electric dipole radiation. You just replay. You can use the same formula, and it's exactly the same with the same coefficient. Magnetodipole radiation, it's like 2/3 times. I'll ask you, how is the energy loss of this thing, magnetodipole radiation? How do you think it scales with omega? If I double omega, what happens with energy losses? It's a kind of simple test whether you remember the most important formula in astrophysics. Dipole radiation, because all radiative processes are essentially calculated as dipole radiation in different ways. Like synchron radiation would be electron moving around the magnetic field line. Curvature radiation, as you move along the field line, and your curvature means that you have acceleration, charge is accelerated. You apply dipole formula all the time. Free or Bremsstrahlung, same thing. Electron is deflected by ion, and that means that you have a charge that is accelerated that produces dipole radiation. So the dipole formula is everywhere. If you want to remember one formula in astrophysics, you bet on, if you're interested in theoretical astrophysics at all, if you're just an observer, maybe, even for observers, I would say, it's nice to remember that. So how do you think it scales with omega? The energy loss of magnetic moment, well, imagine it's a dipole moment, electric dipole moment, not magnetic dipole. If it's rotating with omega, it emits Poynting flux. How does it scale with omega? Yeah, dwarf. To the 4th, yes. Why? That's the formula, yeah. Because it's double, it's the second derivative of mu squared. So second derivative, I have this formula. How does it scale with mu, by the way?
Mu?
With mu, yeah. Okay, so mu double dot squared, right, divided by c cube with 2/3, right? So it scales as mu squared. When you have periodic motion, you just replace mu double dot with omega squared, essentially, times mu. And then you take the square. You get omega to the 4th times mu squared. So that's the simple formula. Whatever the exact numerical coefficient is actually close to unity. The losses of energy losses of a rotating Neutron star with some magnetic moment mu is simply mu squared times omega to the 4th divided by c cube. That's it. And it's a pretty accurate formula. Now, of course, this model is not quite right because it assumes vacuum. This applies to vacuum. And so when you look at what happens with electric fields in this electromagnetic wave that is emitted by this rotating magnetic moment, there will be electric field component along the magnetic field lines. And this electric field component is going to extract particles from the surface of the star and push them to very high energies. If you just solve this little problem, electrodynamics, you will find it. And it was done by Goldreich and Joule in 1968, and actually even before that there was a paper. So you find that probably there will be not exactly vacuum around the star, because there will be electric field that sort of sprinkles particles into the surrounding, and these particles will try to screen the electric fields. The plasma that you eject will try to screen the electric fields. So then historically they look at the opposite limit. So you can calculate how much energy this rotating object is losing in vacuum, but you can also look at the opposite limit when you have a lot of, let's say, sufficient plasma to completely screen out any electric field component parallel to B. So basically, you don't want to apply any acceleration to the plasma. Okay, so here I should mention that because the fields are so strong, the typical fields of Neutron stars 10 to the 12, 10 to the 13, or even higher, Gauss magnetic field. And so if you put particle in this magnetic field, of course it will immediately relax to the ground Landau state. It's going to move only along the magnetic field lines. It's not going to rotate around magnetic, just because you radiate away very quickly in the perpendicular momentum on a time scale which is orders of magnitude shorter than the light crossing time of the system. And so the particles move like beads on a wire. And in this situation, of course, the interesting component of the electric field is the one along magnetic field lines. That's the component that can accelerate particles along these rails. In particular, electrons are light, and also protons are sufficient light here. And the fields are strong. The scale is magnetic field. Roughly, the field you can estimate. What else would you have in this problem? You have magnetic field, you have rotational velocity, and from this you can roughly estimate the fields that you can induce by rotation, V cross B formula. V cross B over C, that would be the characteristic electric field that you can generate by rotation, like unipolar inductor. This is an enormous electric field because B is enormous, and velocity of rotation is also quite high. And these enormous electric fields will push particles to enormous Lorentz factors, like 10 to the 10th, if you don't screen the fields. And these particles will begin to radiate gamma rays due to so-called curvature radiation, the one I just mentioned, right? So if you have a particle moving on a rail and the rail is curved, the magnetic field, like you mentioned dipole field, the magnetic field lines are curved, so they produce dipole radiation. But because gamma is so high, the frequency of that radiation will scale as gamma cube. The photons that are going to emit can be GeV gamma rays. And these GeV gamma rays don't escape this strong field, 10 to the 13 Gauss or 10 to the 12. They convert to electron-positron pairs. So you have an efficient mechanism which taps into the rotational energy and accelerate particles, and eventually leads to an avalanche of creation of electron-positron pairs, okay, which tends to screen out the electric field. And so this pair plasma is quite light, And you expect the system to self-regulate roughly, so it provides some plasma to screen out any electric fields that are responsible in the first place for the acceleration of the particle. This mechanism is going to buffer the particle acceleration. And so the second approximation here is just insisting that there is no electric field, just taking the limit when there is no parallel component in electric field. Just basically pretending that the process of producing this plasma is so efficient that the electric field component that is parallel to B, that is needed for its operation, is negligible actually. So E is much smaller than you would naively estimate from this V cross B formula. And so then you make this, well, this was what they call force-free, the force-free model of magnetospheres. The plasma, by the way, the amount of plasma that you need to screen out electric fields is tiny in the sense that the total rest mass of the plasma times c squared is many orders of magnitude smaller than b squared over 8 pi. Okay, so the magnetic field energy is much greater than the plasma rest mass or kinetic energy. So it's also force-free in that way. Plasma inertia is not really important. Plasma only serves as medium that conducts currents, but it provides no inertia. And that leads to so-called force-free electrodynamics, where basically electromagnetic field kind of plays a game with itself in the sense that the stress energy tensor of electromagnetic field has no sink. So the divergence of stress energy tensor of electromagnetic field alone is 0. Because plasma has 0 inertia, essentially it cannot accept any momentum or energy. And so the only difference it's the same condition as in vacuum, but the only difference from vacuum is that you have now currents. Okay, you cannot lose any energy and momentum from the electromagnetic field, but doesn't mean there is no current. So you do have the source terms on the Maxwell equation. That's the force-free electrodynamics, qualitatively. All right, so what happens in this force-free magnetosphere is very simple. You have the rotational velocity, which is just co-rotational velocity with the star. So omega cross r, right? So, and the plasma is co-rotating with the star. Okay? If you know the magnetic field, you know the field has been screened and the plasma is, you kind of extend the star if you like, but with no inertia. So there is a heavy object in the center, then you add more plasma around it. It has no inertia and it just keeps rotating with this central heavy object. And the electric field you can find immediately from this. You know rotational velocity, you know B, you take V cross B and you find the electric field. Another way to formulate this condition is that the electric field in the rest frame of the plasma is 0. So E plus V cross B over C, that's how you transform electric field from lap frame to the rest frame of the plasma that is moving with V rotation, is 0. All right, it tells you also that at the radius where V rotation is equal to C, that's called light cylinder. So rotational velocity is omega r. So when you go to sufficiently large r, omega is fixed. You come to the speed of light. So this is the light cylinder, simply proportional to omega. And at this light cylinder, the electric field is approximately equal to the magnetic field. Just from that formula, E is negative V cross B over C. Well, V is of order of C, so that means E is of order of B. And that gives you an immediate estimate without looking at details of these force-free models, which are rather complicated. Just understanding that the electric field is comparable to the magnetic field at the light cylinder, you can immediately estimate what the energy losses of this object should be. Because you're interested in the end in the Poynting flux, E cross B. And E is about equal to B. So E cross B over 4 pi, the Poynting flux from the system, is basically B squared over 4 pi times the speed of light, B at the light cylinder. And then you multiply by the area of the light cylinder. Or you can pretend it is a sphere if you're not interested in numerical coefficient. And you get immediately the net Poynting flux from the system. That's what highlighted at the formula at the bottom, right? C times the B light cylinder squared, well, divided by 4 pi, but you can multiply by 4 pi if you pretend 4 pi r square area. And then you end up with exactly the same formula as the vacuum dipole, right? which is not surprising because what else would you get dimensionally? It has to be a combination of mu, omega, and c. But even numerical coefficient is the same. Now, the one important difference is that if you have alpha, the angle between omega and mu equal to 0, the vacuum formula would give you 0 energy loss, because you change mu only if you have non-zero angle, right? If mu is aligned with omega or anti-aligned, mu is not changing with time. So mu double dot would be 0, would be no losses. While the force-free model, all these arguments remain the same. So even if you have aligned rotator, you have plasma around the star, you do induce electric field, you do produce Poynting flux. And that's the more realistic picture. Even an aligned rotator is actually losing energy. And this is how much energy it loses. This is precisely the Crab power, which nicely matches the Crab nebula observations. Okay, what do we observe from these objects? They are rather wild, right? So what is shown here, well, on the left is just the schematic picture of a pulsar. So we know they observed as radio pulsars. That is, there is a radio beam which is rotating together with the magnetosphere, and if it crosses our line of sight, it produces a radio pulse. This is radio pulsation. The mechanism of these radio pulsations is still not quite understood, because it depends on complicated plasma, collective plasma physics, but hopefully there will be some progress on that soon. I will discuss it briefly in a minute. They obviously also produce lots of electron-positron pairs and eject them into the nebula. From observations, we know that you need, in the Crab nebula, we need roughly, well, the usual way to scale it, you can calculate how much current, electric current, is flowing through the magnetosphere. I'll come back to the number of pairs in a second. But first, one note on electrodynamics. Oops. So you have dipole field. This is a neutron star. And you have a light cylinder. And I mentioned here that electric field here at this light E is comparable to B at the light cylinder. Another thing that happens at the light cylinder is that there is a toroidal component. This is a poloidal cross-section of the magnetosphere. There is a toroidal component of the magnetic field, which is also comparable to B at the light cylinder, an electric field. So this toroidal component has to be, by Stokes' theorem, it has to be supported by electric current, poloidal electric current. And this is what they usually call Goldreich-Julian current, after Goldreich and Julian paper in 1969. And so this electric current I can be divided by electron charge to get the number of particles that have to be, the minimum number that have to flow through the system per unit time. So normally, the number of particles that we observe in, say, in the Crab nebula, but they think are ejected into the Crab nebula per unit time, is normalized to that number flux due to circulation of the current in this system. And the ratio of the two is called multiplicity. So the multiplicity is a kind of number that shows you how many electron-positron pairs are overproduced by this machine relative to the minimum number that you need to sustain the electric currents in this system. And this number is huge. Multiplicity in the Crab nebula is about 10 to the 6, a million. So it's an extremely efficient machine of electron-positron pair creation. So that's one thing that we observe. Okay, second thing, the first one was radio waves. Of course, we also observe a very broad electromagnetic spectrum, which extends from radio all the way to GeV band. And here on the right, you see the panel with several spectra of different young pulsars. And you can see huge differences between different objects. And in principle, so recall that I'm talking about something really simple from physical point of view, right? So we have, again, we have a sphere which has omega and mu. That's all it's got, okay? In addition, there may be one parameter which is the viewing angle, but that's it. So you can view the system from different angles. And this simple machine is producing quite diverse phenomena. So obviously there is significant sensitivity to maybe from where you view it. Maybe it's sensitive to the angle between mu and omega. And maybe it's sensitive to the values of mu and omega. Okay, but there's nothing else in the system. The size is pretty much fixed. So you just have rotation and magnetic moment, that's it. Okay, so one observation, of course, here, these two models that I talked about, the simple models, the vacuum model and the force-free plasma field magnetosphere, of course, they cannot produce any emission, right? Because, okay, in the vacuum model, there is no particles around the star to emit anything, so it's completely silent. This model would give you zero emission from the object. In the force-free plasma field magnetosphere, you have lots of plasma, which screens out the electric fields, but there is no electric field which could possibly accelerate the particles. So there is no dissipation in that system. It's dissipation-less. This is what force-free is. So it's, again, completely silent. So there is no way to test this kind of models against the data until we relax this approximation and actually try to understand what is the deviation of the real system, what is the electric field, what is the non-zero electric field, where is this gap, electric gap, which creates this electron-positron discharge, and what is the voltage that is responsible for this discharge, and what is the power that is dissipated in this discharge, where it is located, what is its power, how much pure multiplicity would produce. That's the kind of physics questions you have to answer. And the only way to answer these questions is actually to include explicitly the plasma into the picture and try to solve it self-consistently. Okay, so there has been significant progress. By the way, I don't have, how much time did I spend? 20 minutes left. Do you want me to stop sometime before you have any discussion?
Like you could spend more time for questions.
Maybe 30 minutes.
20 minutes to talk.
20 plus questions.
Ah, okay. Right, so let me talk about recent developments in this field that Sasha in particular contributed a lot to. And so the development is an attempt to understand, and successful attempt to understand this physics problem from first principles. So the idea is very simple. You just try to do a numerical experiment, a direct numerical experiment, which explicitly follows how particles are moving in the electromagnetic field of the star. So the plasma is part of the simulation. Matthew Kuntz already discussed the PIC method, particle and cell method. That's the method that is used for this type of simulation too. So you model plasma as a collection of individual particles. There may be 10 billion particles in the computational box. But what you try to do here is to find a self-consistent solution for the plasma motion and the electromagnetic field evolution. So basically, in these boxed equations, you can see the equation of motion of particles. P is the momentum of the particle. E plus V cross B over C is the force that is applied, electromagnetic force that is applied to the particles. In addition, there is gravity. Gravity is important where electric field is not. So when you come to the layer of high density on the surface of the star, electric fields are screened out because of high density. There, gravity is important. It's responsible for sustaining the hydrostatic atmosphere. By the way, the scale height of hydrostatic atmosphere on a neutron star is tiny. If you have 1 keV temperature, 10 to the 7th Kelvin, it's nothing compared to 1 keV is nothing compared to the escape energy from the star. So the scale height of hydrostatic atmosphere is typically a few centimeters, much smaller than the radius of the star, very thin layer. dense and thin layer. It just serves as a source of plasma particles for the magnetosphere that can be lifted, extracted from there by the electric field. And so what you do in this numerical experiment, you take this ball of plasma, say, metallic ball covered by dense plasma layer, and start with initially, let's say, dipole field, simple dipole field. In the simplest configuration, you would talk about a line rotator when you are going to spin up the star along the magnetic axis. And then you start to spin up the star. And you're trying to solve the equations, which are the equations of motion for particles, and then the two Maxwell equations, the two equations for the magnetic field and electric field, right? Try to do this self-consistently. The way it's done, you discretize the equations for electromagnetic field on a grid, and you follow particles individually. So that's why it's particle in cell method. Cell for the grid of electromagnetic field. But to evolve electromagnetic equations, you have to calculate the electric current that is provided by the individual particles that you track there. So you know the motion of each particle, you know the electric current that they create. You need, of course, enough particles to have sufficiently good statistics to have good representation of the electric current. Of course, in a real simulation, the number of particles is much smaller than it would be realistically. So you can think of simulated particles as macroparticles. It's like the clumps of plasma, if you like. All right, and then you just take the system, spin it up. You begin to use electric fields, and then this electric field begins to lift the particles from the surface, and then you see all the physics that I described before. So the particles are going to be accelerated by these electric fields. Then, if you include in this simulation the relevant radiative processes, in particular this curvature radiation, where the particles radiate gamma rays, and then you trace these gamma rays and see how they convert to electron-positron pairs, you are supposed to explicitly see the electron-positron discharge. And that's the way to figure out where this discharge happens from first principles. You don't assume pre-assume any location for this discharge. You're supposed to see how the system self-organizes to supply itself with the plasma. So this has been done. I'll show just one run for the simple line rotator. So what you see, the beautiful white circle in the center is the Neutron Star. The two dotted lines show the light cylinder after spin up. So initially the light cylinder is at infinity because omega is 0. And the green curves are the magnetic field lines. So initially just a dipole field. And now now there is no color, right? Black because there is no electric current. The color is going to show the electric current flowing in the system. In particular, this radial component in spherical coordinates. So red means positive current, right? That means ions or positrons are flowing away from the star, or electrons flowing back to the star. That's the positive radial current. And blue means negative current. That means electrons flowing away from the star, let's say. And let's begin to spin up. And let's see how you begin to launch these currents. And interestingly, you can see two signs of current immediately, blue and red. Of course, in the end, when you find quasi-steady state, the two currents have to be equal because you cannot charge indefinitely the star. And then you see how the system relaxes to this beautiful configuration with the Y-shaped current sheet. So you see the Y point close to the light cylinder. And then you see a lot of blue. That means electrons flowing out from the polar cap. And there is a positive current, which could be ions flowing out along this current sheet. The inside the light cylinder, we would usually call it a separatrix because it goes around the zone of closed field lines. You see the green curves, the magnetic field lines are closed inside the light cylinder, and they are open outside the light cylinder. Those field lines that cross the light cylinder, they get open and go to infinity. And so the current sheet goes around this closed zone. And of course, there was nothing enforced, imposed on that system, right? It finds itself the state that allows, that is self-consistent. Now, what is not shown in this figure is where the discharge happened, but I can tell you, so I don't want to spend too much time on that. The discharge is happening in the current sheet, in this red part of the simulation. So you have a lot of pairs created, in particular around the Y point, and also in the equatorial current sheet outside the Y point, there is a lot of pair creation with high multiplicity. Not million in the simulation, you cannot do million because you have to rescale these numbers, but tens to hundreds you can do. So that's what you see, the relaxation which was predicted before in these force-free models. Before I show the force-free models, this is 3D snapshot, right? So before I showed the poloidal cross-section, now this is the 3D picture, a snapshot, a 3D snapshot of the same simulation. Again, you see the star, but now the color here, and you see the green curves, which again, the magnetic field lines, but you see the toroidal component as well, right? The twist of the magnetic field lines. The field lines are almost dipolar inside the light cylinder, and as you approach the light cylinder, they become more and more twisted, and outside the light cylinder, they go like a spiral, and then they form this pointing outflow, the wind from the system. But the color also shows here, this orange and blue, shows the charge density. So charge density is negative where it is blue, and positive where it is orange. So you can see how the system relaxes to this non-trivial state where this current sheet enveloping the closed zone is negatively charged, and the equatorial current sheet is positively charged. The only reason I'm showing you this is that this is beautiful physics, which is recovered from first principles, and it's a bit complicated. I don't want to go into the details, but to appreciate that, I think it's nice to see that there is a certain structure that comes from non-trivial structure, non-trivial electrodynamics. Again, remember, it all comes from a ball rotating with omega and some magnetic moment. That's it. So it self-organizes through this discharge. It finds where the discharge should work, and then it forms the self-consistent state of plasma and electromagnetic field. This simulation does not include GR. Later, Sasha did simulations with including general relativistic corrections, and then they found that also the discharge can operate above the polar cap, where you have sufficiently compact star. And they also did 3D simulation. I have, I think, a slide on that. But this is summarizing the previous pre-peak view of the force-free models, which does not tell you where you have the discharge, but it tells you the structure of the electromagnetic field, which is pretty close to what we see in peak simulations. So it is basically, to the first approximation, the system is electromagnetic configuration is close to force-free configuration, and the peak simulations allow you to see what plasma is doing, how it works to sustain this this force-free configuration. So you can see the current sheet, the Y point, the inner closed field line zones, and the open field lines. Now, the wind that goes to the Crab Nebula is, of course, these open red field lines, where it forms this tight spiral, and it flows away in this completely Poynting flux dominated electromagnetic wind. What you see from peak is what the plasma is doing and where particles pick up energy. And so the left panel here shows the motion of the ions. More specifically, the color here shows the energy of the ions. So yellow means high energy ions. Why ions? We chose to show ions here because ions are like markers. They don't lose energy to radiation. They're massive. Electrons can lose a lot of energy as they pick up high Lorentz factor, but they also radiate emission. Ions don't radiate anything. They're heavy particles. And so when you look at ion energy in these simulations, you can measure the voltage essentially. How much energy they picked up is the gap voltage. So the gap produces a lot of pairs, but it also accelerates whatever ions are flowing through the system. And you can see how ions nicely accelerated along the current sheet and how they come to the Y point and begin to gyrate, these two motions. It's just basically gyration. Remember, there is a toroidal component also. They gyrate around the B5 field. And basically what the system is doing is that, on the right panel you can see that, it ejects plasma ions and produce electron positron plasma. It's like a nozzle. It's a magnetically dominated nozzle. So it ejects a lot of plasma in the equatorial plane. So blue on the right panel means that magnetic energy is far dominant over plasma rest mass energy. Like I told you before, magnetic field is energetically dominant compared to the energy of the plasma. But there is a region where plasma dominates. Plasma has more kinetic energy. And so, like magnetic field lines form, if you like, it's like elastic nozzle essentially. You can push the boundary of the nozzle a little by the pressure of the plasma, but the plasma wants to fly out. You have rotation, you have some electric acceleration, and it ejects this plasma in the equatorial plane. Another thing that is happening in this current sheet is reconnection. It's a nice setup for studying magnetic reconnection also. It happens naturally because the reconnection current sheet is formed not just by some arbitrary boundary condition, as many peak simulations do. When you study, you just take a box, computational box, 2 magnetic fluxes, and you could study driven or spontaneous reconnection, but you start with an initial condition and some boundary conditions, for example, periodic boundary conditions. And you could also question whether whether it's a good representation for the, for whatever realistic problem you are looking at. Here you set up the reconnection current sheet outside the Y point naturally. This is what it should be in reality. And so you can see how plasmoids form there and how you have the so-called kink mode, etc. This is a 3D. Remember, the line rotator only corresponds to, what you can do in axisymmetry is in line rotator or anti-aligned. If you have an angle, you break the symmetry. And of course, real pulses, in order for real pulsar to pulsate, you have to break the axial symmetry. Otherwise, whatever angle you are looking at, it's not going to pulsate. Right? It's the same, as it rotates, it doesn't change the emission. So when you break the symmetry, you have to do 3D simulation, and you find that something similar for small angles between mu and omega, and then significantly different configuration when you have almost perpendicular rotator. And you can see here again current, but in this case J parallel along the magnetic field lines from Sasha's simulations with 3D. You can see how the fields also creates this. The current sheet changes its shape, so it becomes wobbling like that because of this inclination. Right? So 3D is more interesting. But again, pairs are created in the equatorial current sheet, and out, in particular around the Y point and outside the Y point. So I spend a lot of time on rotation. I'm still very far from magnetars, from the main topic. Let me say a few words about accretion. For accretion, I just wanted basically to remind you things that I'm sure you know, that neutron stars accrete, and they can become very bright sources of radiation. And actually, the first observational discovery of neutron stars, which was in 1962. It was before the discovery of pulsars in 1967. And it was an X-ray discovery. It was a balloon experiment where they saw actually the brightest object in the X-ray side, Scorpions X1, Scorpius X1. And moreover, Shklovsky realized that this object, this X-ray source, is a neutron star in 1967, again before the discovery of pulsars, radio pulsars. This is an extremely bright object, 10 to the 5 solar luminosities, right? 10 to the 5 solar luminosity means 2 times 10 to the 38 ergs per second. And it's actually close to the Eddington limit, right? So the Eddington limit, which is written here below, again, to remind you, I hope you know that stuff, right? So you have the maximum luminosity that you expect. It is in the simplest naive models of accretion. You expect the maximum luminosity from the fact that if accretion provides too much power, too much radiation pressure, it begins to push the stuff away, and you cannot accrete anymore. So there is an upper limit, which is called Eddington limit. It scales with mass of the accreting object. And for solar mass, or Neutron star mass, it's about 2 times 10 to the 33 ergs per second. That's the luminosity of Scorpius X1. So it accretes close to the Eddington limit. Of course, it's a binary system. You need a donor. You form the accretion disk. And there is also a jet in the system. Very many objects we see that now in Neutron stars, not just black holes. And here I just have, I think, one slide for accretion. I wanted to highlight the recent development, which I think is the most exciting development in the theory of accretion. It's the discovery of ultraluminous X-ray pulses. And some of you I know very well and work on this topic, actually. So, of course, what accretion does is, first, I have a few remarks. Obviously, it increases the Neutron star mass if it can, if it provides a lot of material over a long time, let's say age of the Neutron star. It can spin up, in some cases spin down the Neutron star, because it provides or removes angular momentum depending on how you accrete. You can accrete simply through the disk all the way to the star, or if the Neutron star has a magnetosphere, you can begin to accrete at larger radius and fall along the magnetic field lines, and then the lever for angular momentum will be different. So there are different regimes of accretion. So yes, and you also can have X-ray bursts powered by nuclear burning in these objects. Now, this recent exciting discovery, of course, is like many exciting discoveries, was kind of accidental. NuSTAR and other telescopes, and NuSTAR in particular, looked at galaxy M82 when there was a supernova. And in the field of view, it turns out that there was a very bright object in ULX, which people not knew before. But it turned out that this object is pulsating with a period of, this is what NuSTAR saw, it's pulsating with a period of 1.37 seconds. With such a short period, so people before, when they talked about ultraluminous X-ray sources, of course, what we call ultraluminous X-ray sources are the sources with luminosities exceeding the Eddington limit. And people, the one interpretation was that you have black holes accreting with high masses than just a few solar masses, and that's why the luminosities are so high, because the Eddington limit is high, it's proportional to mass. And it was surprising, and okay, there were some models, like I says, like in our galaxies, when you have it says 433, when you have a lot of luminosity coming from the accreting black hole, you can try to come up with models with super Eddington, moderately super Eddington luminosity from black holes of moderate mass. But no one thought about Neutron stars. So the fact that it is pulsating unambiguously tells us that this is its perfect period, that this is something rotating with that period. And the only objects we know that can do that with such short periods are Neutron stars. For example, white dwarf cannot rotate with 1.37. It would be disrupted by centrifugal forces. Okay, that's too short period for a white dwarf. And the luminosity is enormous, 10 to the 40, so it's like 50 Eddington limits. And more recently, looking at the archival data, Israel et al. Discovered that there are two more ULXs, and actually one of them is even brighter. So all that is exciting because no theories predicted that. So basically, these things should not exist with first approximation. They violate accretion physics. And so, like hundreds of Eddington limit, there was a paper by Basko and Sunyaev, a classical paper, and a few follow-up papers later, where they actually, the main point was to calculate the maximum luminosity from an accreting Neutron star. And they would find that it's like several times Eddington limits, maybe 10, but no way of getting hundreds. And it's still an outstanding problem. So one promising direction is it's maybe an accreting magnetar, which has very strong field. It helps somewhat, but it's still difficult. When you look at detailed models, a bit difficult to explain these high luminosities. And it cannot be strongly beamed, so beaming is not really helping here. Okay, I think I used up most of my time now. Yeah? Okay. So I'll stop. If you have questions, you ask question now. And then later I will discuss, move toward magnetars gradually.
Questions? I know that magnetic reconnection has been proposed as a method for particle acceleration, but can it accelerate particles to ultra-high energies, and does it scale with mass?
Yes, it can accelerate to ultra-high. What do you mean by ultra-high energies? Yeah, you mean this particular object, the pulse set setting. It is an accelerator. The energies are high, but also radiative losses, by the way, especially for electrons. So in the end, I would say, okay, so you can estimate the characteristic electric field that is accelerating particles. And you can estimate the characteristic energies that you can expect from particles accelerated, let's say, at the light cylinder. And without screening, you would get to very high Lorentz factors, but realistic, for young pulses with realistic screening, typically these are millions, gamma 10 to the 6th, 10 to the 7th. Of course, in the simulations, we don't see that because we have to rescale this gamma. But yeah, I mean, yes, it's an efficient accelerator. There are primary particles, what they call. There are secondary plasma, which creates an avalanche of pairs of low and low energies. Because you meet, what happens is that you have these primary particles that tap into the full potential drop and reaches, let's say, electron reaching Lorentz factors of 10 to the 7th, which is huge. Then it emits gamma rays of many gamma rays of much lower energies, GeV energies, and those gamma rays convert to secondary pairs of GeV energies, Lorentz factors, let's say hundreds or thousands. But these primary particles, the maximum voltage gap, they go up to 10 to the 7th typically.
I think he also asked about acceleration in the connection. How much that is efficient?
There are different types of reconnection, right? So in the crop, you have reconnection near the Y point, and you have reconnection in the nebula at the end of the wind. So I don't know, what would be the best estimate for the maximum energy in near the Y point? I'm pretty sure you cannot go above 10 to the 7th, because it's like still limited by the same arguments, like voltage, it's similar. Outside,
For ions, right? Like you can do more for ions.
you could do more for ions, but you screen voltage by the same mechanism. So you still, the gap voltage is still the same, right? So the threshold for accretion kind of sets the upper limit for energy. When this wind comes to the outage, it's a different problem. I'm not sure what is the maximum energy there. But yeah, I'm not sure how general your question is. In reconnection studies, we have a lot of simulations now on the topic where they just actually try to answer that question. You just put two magnetic fluxes next to each other, there is a current sheet between them, let them reconnect, and do the peak simulation and see individual particles, how they are accelerated. And the mean energy per particle is related to the sigma prime, that's the ratio of magnetic energy to the plasma energy. And the maximum energy in the simulation is actually limited by the time of the simulation. The tail keeps growing.
Sorry, what are the mass accretion rates on these X-ray pulsars? What do they think they are?
The mass accretion rates, the accretion rate, you know it from luminosity, essentially, within moderately uncertain factor due to moderate beaming. But essentially, at least, well, I mean, you could try to hide some of it, but most of, in neutrino emission, but most of it has to, matter settles to the Neutron Star surface and creates in gravitational potential well of 0.1 c square specific energy. So if you observe 10 to the 40 ergs, you divide it by 0.1 c squared to find out how much mass has to go through the system to accrete, to produce observed luminosity. Unlike black holes, which can, eat this energy together with the mass, here typically you radiate this mass, this energy away. So the efficiency is basically controlled. The translation of mass accretion rate to the observed luminosity, basically efficiency is 0.1. It's set by the gravitational potential on the surface of the Neutron star. Yeah.
Could you please show again the dimensional simulation? Yeah.
Here's simulation. Okay.
Yes.
Yeah.
Because the left panel is like the movie you showed before, more or less. The left panel.
Yeah.
But the right panel, I didn't understand exactly how does it work, because it should be like seen from like one of the balls. Yeah.
Sasha will explain to you.
You should pull out the 3D structure. I mean, this is, so there is a magnetic moment. It's rotating around. And in this, if you jump into a frame which correlates with the magnetic moment, you'll see a quasi-stationary picture.
That's that one.
This is this one.
But in that case, the magnetic momentum is aligned with the rotation axis, or no?
No, it's
No.
not. It's,
okay.
it's tilted by 60 degrees.
How much? 60.
60.
Okay.
Basically, you see the blue and red. That's the magnetic moment, the field line. You see the
Okay.
Roughly where there is a maximum current out, the maximum of this blue current in the northern hemisphere is where the magnetic moment
So you have this is like a polar picture
Yes.
in a moving reference frame.
It's not a moving reference frame, but it's co-rotating.
Yeah, co-rotating,
It's
yeah.
a frame,
Co-rotating.
phi prime equal to phi minus omega t.
Yeah, I want to, yeah.
So in that frame, it's quasi-stationary, and that's what's shown.
Okay.
yeah. I know.
Do we have any theoretical expectation for the distribution of rotation and B field angles?
Obliquitous.
Yeah, the angles between mu and omega, between magnetic moment and there are theoretical arguments. Sasha again worked on that, although there are some questions I think to your work. Yeah, so I don't. Yeah, there are theoretical. There's a lot of thinking about how these things should evolve. If you come with some configuration after the Neutron star birth, you would expect the angle maybe would evolve over time, and maybe it will find the preferred configuration. Let's say orthogonal rotator, which means perpendicular to omega, maybe line rotator, some angle. But I don't think there is, by now, there is an established prediction for what the distribution should be. Is it fair summary? Or?
I mean, it's a convolution, for burst distribution and evolution. So what happens at the burst is pretty uncertain, I think.
The burst, sorry,
Burst.
at birth. Oh, yeah, it's a convolution with the, yeah. I think it's uncertain also what happens with what happens later, maybe. But for birth, we don't know anything really about the magnetic field.
Did you simulate orthogonal case, and whether you obtain the same result as Sasha's? Actually, we have no current sheet in this case.
We haven't done orthogonal rotator yet. We are still trying to do really well the axisymmetric rotator, which does not pulsate. Yeah, so, yeah, I don't know. Yeah.
Any more questions? Okay, if not, let's thanks Andrei again. And